Hi, I'm Jim Burnham. Welcome to Chapter 4 in General Chemistry, Problem Solving. Now, do you like word problems? most people don't. Look at this. Vera and Vicky are sisters. Vera is 4 years old and Vicky is 13 years old. What age will each sister be when Vicky is twice as old as Vera? You love these, right? From your math class? Most people don't. Now, few chemistry problems will be this tough, but we are going to have a problem-solving plan when we come across word problems. There will be complex problems that need to have a plan. So it's kind of like planning a trip, right? You take a road trip from one side of the country to the other. You need to know where you're starting. You need to know where your finish line is, and you need to know how to get there. So that's what we're going to focus on today. Basic problem-solving skills, a strategy to get you to the goal line. We're going to take a three-step approach with the acronym ACE. And ACE stands for Analyze, Calculate, and Evaluate. Those are the three steps that we will apply in all of our problem solving. Analyze, Calculate, Evaluate. So let's take the first step, Analyze. We're going to list all of our givens, all of our knowns and our unknowns. I'm just going to write them down clearly so we can know where we're starting and what we're trying to solve for. Don't skip this step. A lot of people say, oh, no. Write them down. The more you write down your knowns, your unknowns, the clearer it will be what formula you need to use and what it is you're actually trying to solve for. The next step is, of course, to calculate. Once you've figured out what you've got and the proper formula to use and what you're trying to solve for, then you're just going to plug all that information into your formula and then plug and chug. You're going to solve for the unknowns. And the final step, and this is important not to skip this, do your results make sense? Is it what you would estimate? Is it a large number if you're expecting a large number, or a really small number if you're expecting a small number? More importantly, have you used the right units? You've heard me say over and over again, right? A measurement without a unit is useless. A number without a unit is useless. It's nonsense. Have you used the right number of sig figs? Have you applied your sig fig rules correctly? So let's look at a sample problem here. What is the mass in grams of a piece of lead that has a volume of this many cubic centimeters? All right, so we're going to analyze. We're going to list our knowns and our unknowns. What do we know? Well, we have a volume of lead that's 19.84 cubic centimeters. We also know what density is. We know the density formula. The density is the relationship of mass divided by volume. Now, the density of lead is not given in this particular problem, so we might have to look it up. We have this earlier in the text, and we can find the density of lead as 11.4 grams per cubic centimeter. So that's another one of our knowns. Don't be afraid to use the internet or other resources, reference books, to get what you need if you need something. So now what are we solving for? Well, what is the mass in grams? So that's our unknown. So now that we have the volume of lead and the density of lead, right, we have 2 out of the 3 things in the density formula, well, we can solve for our unknown. And so we can rearrange the equation from density equals mass over volume and solve for mass. And mass, we're just going to multiply both sides by volume, and it's going to be volume times density equals mass. So that's what we're going to use. So then we just plug in what we know. Mass is going to be volume, 19.84 cubic centimeters, times our density, 11.4 grams per cubic centimeter. Notice how our cubic centimeters are going to cancel, which is what we would hope for, so that our answer is in grams alone. That's what we track mass in, is grams. So our calculator gives us the number 226.176 grams. Well, we say, can we keep all those numbers? No, because we only started with 4 sig figs here, 3 sig figs here. So our answer, we can only keep 3 sig figs. So we got to round this to the closest, the nearest 3, the first 3, and so it'll be 226 even grams. Does this answer make sense? Yeah, they asked for the mass of lead, and we found an answer in grams. Our units canceled, and the numeric value makes sense because of the sig figs. So we're fairly confident that we've done this problem correctly. Let's look at another sample problem. What is the volume in cubic centimeters? So that's where we're going to try to find, that's our unknown, of a sample of cough syrup that has a mass of 50.0 grams. So we're going to write that down, that's unknown. And the density is also given here, 0.95 grams per cubic centimeter. So our knowns are the mass of cough syrup, 50 grams. The density, we know our density formula. We're trying to solve for volume of cough syrup in cubic centimeters. So you can see that we have 2 out of the 3 things that we need from our density formula. We're just going to solve for our unknown. In this case, we're going to solve for volume. So we're going to get volume up here by multiplying both sides by volume. And then we're going to divide both sides by density to get density down here. And we're going to end up with volume equals mass over density. And then we'll just plug in our numbers and calculate. So that's here we are here. We know this. We're going to rearrange our density formula according to our needs. We're going to plug in our knowns, our known values. We're going to see that our grams are going to cancel on both sides. And since we have a denominator in the denominator, it's going to jump up here to the numerator. And we're going to get an answer that's 52.6316 cubic centimeters. Can we keep all of that? No, we can't. We have 3 sig figs here, 3 sig figs here. So by the rules of multiplication and division of sig figs, we can only keep 3 sig figs. Now we evaluate. Does our result make sense? Well, yeah. This is a manipulation of our density formula. Our units canceled the way we'd expect to give us volume units, and our sig figs have the required number of sig figs. All right, and this takes us to really the heart of the chapter. This chapter, problem solving, is all about conversion factors. We can express quantities oftentimes in multiple ways. So I can say $1 is the same as 4 quarters, and that's the same as 10 dimes, and that's the same as 20 nickels, and that's the same as 100 pennies. Those are all equivalent amounts. And the same goes with scientific quantities. We can say a meter is equal to 100 centimeters, which is also equal to 1,000 millimeters. So we can use different units to express the same length. These are all equivalent lengths, just expressed in different units. And that's going to become important. This difference in units is going to help us when we want to change from one unit to another. So 2 equivalent measurements can make a ratio. A ratio is when we simply just put one of those in the numerator, one of them in the denominator. That can make a ratio called a conversion factor. If you have 2 equal measurements, you can combine them into a fraction, a numerator over a denominator. And that's called a conversion factor. So essentially, it's the fraction made from an equality. Right? So here's some examples, right? We know these are equivalent, so I can put 1 meter over 100 centimeters because they're equivalent. This is a 1-to-1 ratio. And that's the reason I can flip this with no problem. Since this is a 1-to-1 ratio, this is also a 1-to-1 ratio if I flip the numerator and the denominator. So both of these are perfectly correct. And for every equivalency, remember this, for every equivalency, you can create 2 conversion factors. You just flip them. So you put the meters on top here and then the meters on the bottom here, and vice versa. Every conversion factor can be inverted to give 2 equivalent conversion factors for every equality. So that's super important because that's going to, the version of the conversion factor we're going to use is going to depend on what we want to cancel and what we want to keep. But we have to remember that. We can make a conversion factor from any equivalency. We just stack them as a ratio. And that fraction can be flipped. Because it's a 1-to-1, 1-to-1 ratio, it can be flipped and we preserve the equality. It's a 2-for-1 special. You get 2 conversion factors for every equivalency. So here are some common equalities, right? 1 foot equals 12 inches. So we could say, oh, we could put 1 foot over 12 inches or 12 inches over 1 foot. Those are the 2 conversion factors, conversion ratios that we can create from this equivalency. Same with the yard equals 3 feet. I can say 1 yard is over 3 feet. That's the same as 3 feet over 1 yard. And so on with all of these. Works for US equalities and metric equalities and so on. Notice too that these are all going to be defined quantities. So we're not going to lose sig figs if we use one of these as a conversion factor. If we create a conversion factor, say, between 1 kilometer over 1,000 meters, and I use that and I multiply that, I don't lose sig figs because this is one of those special cases where we have unlimited sig figs. Remember, it's exact counts have unlimited sig figs and defined quantities, like all of these quantities in here. Remember, they can be flipped because they are equalities. Everything on the top is equal to everything on the bottom. So if I flip it around, everything on the top is still equal to everything on the bottom. It's still a 1-to-1 ratio. So again, just breaking this down, I know this is almost too simplistic, but so if we have this equivalency, 1 meter is equivalent to 3.3 feet, we can say 3.3 feet is to 1 meter, or we can flip it 1 meter over 3.3 feet. Okay, 1 inch, 2.54 centimeters, 1 inch over 2.54 centimeters, or 2.54 centimeters over 1 inch. These are all the same. Anytime you have equivalencies, you can create inverted fractions, inverted 2 different conversion factors. Remember, conversion factors provide a comparison for any 2 units. Now this takes us to dimensional analysis, which is just a super fancy word for keeping track of your units. You can solve the most detailed, complex word problems simply by keeping track of your units. And if you keep track of your units, what you're starting with, what you're trying to get to, and you cancel correctly, you cannot help but get to the right answer. Keeping track of your units will make sure you do your problems correctly. So keep track of our units to solve the problems. We're going to plug in conversion factors. Remember, we might have to flip them to get the right thing in the numerator and the right thing in the denominator. But we're going to plug in conversion factors that cancel out the units that we don't want until we wind up with the units we do want. So here's conceptually the idea. You're going to have a given unit, right? And then you're going to use a conversion factor, which is going to have your desired unit in the numerator and your given unit, your starting unit, in the denominator. And that's going to cancel with this unit over here. So the denominator will cancel with this numerator and leave us with a new numerator, which is our desired unit. That's what conversion factors do. They can change units. So here is a sample problem. All right, 600 tickets to a chili supper. You have to make chili. You have a recipe that serves 10. And it calls for 2 teaspoons of chili powder to serve 10 people. How much chili powder do we need for 600 servings? Okay, analyze. We're just going to write down our knowns. We got to make 600 servings. We know that for every 10 servings, the equivalent amount we need of chili powder is 2 teaspoons. You can probably see that we're going to use this here, this equivalency, to make a conversion factor, right? We can say 10 servings per 2 teaspoons of chili powder, or 2 teaspoons of chili powder per 10 servings. What are we trying to find? The amount of chili powder that we need in teaspoons to serve 600 people. Okay, remember the correct conversion factor is going to have our known unit in the denominator, that's the one we're trying to get rid of, and our unknown unit in the numerator. So we're going to set this up like this. Since we're starting with 600 servings, we're going to cancel out servings. So when we make our conversion factor, remember we could go 2 teaspoons over 10 servings or 10 servings over 2 teaspoons. We're going to use the one with servings on the bottom to cancel out the units over here that we're starting with. And that gives us the units that we want in our answer. 2 teaspoons chili powder in our answer. Now we're all set up. Our servings cancel. We get the answer we're looking for, the units we're looking for in our answer. We just do the math. We plug this in, we calculate it, we get 120 teaspoons of chili powder. Does this make sense? Yeah, because we know that 2 teaspoons serves 10 people. 600 people is 60 times as much, so it should be 60 times as much as the amount to serve 10. 60 times 2 is 120. Makes sense. We know that we've kept track of our units correctly. We've canceled out what we started with and didn't want, and we got a new unit in our answer that we did want. So we're very confident that this answer is correct. So you saw how we are converting between units. So let's say someone says, how many seconds are there in a school day? Right? All right, so let's say we have a 7-hour school day. We want to turn that into seconds. So we're going to put our starting point over here, hours, and we're going to put our ending point over here, seconds. And then we're going to say, okay, how many seconds is that? Well, we're going to start by converting out from hours into some conversion factor that we know. Now, maybe we don't know the conversion factor of seconds to hours, but we do know minutes to hours. So let's just start with that. So we cancel out hours. Now we're left with minutes. But we can also do the same thing. We can cancel out minutes with a new conversion factor and then leave us with seconds. So how many minutes are in an hour? 60. Great. How many seconds are in a minute? 60. So you're always going to put the bigger number on the smaller unit because this is an equivalency. And then you're going to see that hours cancel, minutes cancel, and the only thing left are our units in seconds. And that's what we want. We want to be converted to seconds. So we have the answer 25,200 seconds. So here is another sample problem. We want to measure out 1.84 grams of copper wire. The only copper wire available is a spool with a mass of 50 grams. How many students can do the experiment before we run out of copper? So what are our knowns? Well, this is the copper we have. We have a mass of 50 grams. Each student needs 1.84 grams of copper. So we're going to create a conversion factor, right? 1.84 grams of copper per student. We could also flip that around and say, put student on top. Per student, we need 1.84 grams of copper. What are we trying to find out? The number of students that this much copper, if we give this much per student, will satisfy. So we're just going to start with grams of copper, right? And we're going to try to get to students. So dimensional analysis, we're just going to let the units guide us to the right setup of this problem. So we're going to start with 50 grams of copper. And we're going to pick a conversion unit here where copper is on the bottom. So we're going to take this and flip it. Remember, we can flip any conversion factor. And so we're going to put the grams of copper down here so it cancels with this numerator here. And this puts our answer in students. So we do the math on this now, and we get 27.174 students, which means I can give 27 students a full measure of copper, and that's it. I'll have a little bit left over, but I can't do 28 students. So 27 students with a little left over is what I can use. Is how many students can do this experiment. Does this make sense? Yeah, it seems pretty reasonable. If it's basically 2 grams per student, and I divide this by 2, I should get around 25 students. Roughly, that's my rough estimate, and my answer is 27, so that accords with my rough estimation. Okay, this takes us to multi-step problems. Like we saw earlier here, sometimes we have to use more than one conversion factor. So that's what this is. So just like we want to break complex tasks into smaller steps, we're going to break complex unit conversions into small steps. So imagine you're cleaning a car, right? You break it up into smaller steps. First I'm going to vacuum it, then I'm going to wash it, then maybe I'm going to wax it. And so I'm going to take this complex thing and break it up into smaller, manageable steps. That's what we're doing here when we're converting from one unit to another. So sample problem. What is 0.073 centimeters in micrometers, micrometers? Right, so what's our known? Well, we have a length that's this many centimeters. We can express it in scientific notation as 7.3 times 10 to the negative 2. We know that there's 100 or 10 to the 2 centimeters per meter. And we know that 1 meter has 10 to the 6 micrometers. So we want to go from length in centimeters to length in micrometers. So we're just going to start with our given length, 7.3 times 10 to the negative 2 centimeters. Now we're going to, since we don't know how to convert directly from centimeters to micrometers, we're going to go from centimeters to meters, and then from meters to micrometers. So we're going to put the thing we want to cancel down here. So we're going to put 1 meter per 100 centimeters. So now my centimeters are going to cancel. I'm left with meters on top, but I don't want meters, so I'm going to cancel meters again. I'm going to put meters down here with the unit that I do want, micrometers. And now I'm just going to do the math on this. And it turns out to be 7.3 times 10 to the 2 micrometers, 730 micrometers. So do the results make sense? Well, yeah. Even though this is a small number of centimeters, micrometers are much, much smaller, so we should have more of them. And we do. We have 700, which just qualitatively makes sense. We're going to have a whole bunch more of a much smaller unit to be equivalent to this many centimeters. We've canceled out our units correctly, so we're confident that our units are right, and thus the numbers that go with those units will give us the right answer. Okay, we've already done one similar to this. How many seconds are in 1 day? We start with 1 day, right? We just start multi-stepping it down. We get rid of days, we go to hours. That's not what we wanted in. So, okay, so then we get rid of hours, we go to minutes. That's still not what we wanted. So we get rid of minutes and we go to seconds. So here we have 86,400 seconds per day. Do the results make sense? Yeah. I mean, 86,000, we'd expect a pretty big number of seconds in a 24-hour day. And we've canceled our units correctly. Our days have been canceled, our hours have been canceled, our minutes have been canceled, we're left with seconds. So we're confident that our answer is correct. How about converting complex units? Well, what is a complex unit? This is when we have ratios of 2 units. So we have, before, look, we were looking at 1 unit in here in the numerator, day, we convert it to seconds. But we can also have a ratio of units in the thing that we're starting with. For example, speed. We can have something like miles per hour, or density, grams per cubic centimeter. So we can convert both of those units, and when we do that, it's a complex unit conversion instead of just a simple unit conversion. So complex just means more than one. So if we're dealing with 2 units or more, so when we do this, we have to use multiple conversion factors to get rid of the multiple units. So the good strategy is to first convert the units in the numerator to your desired units, and then convert the units in the denominator to your desired units. So here, for example, if we're converting feet per second to miles per hour, we would start with the numerator, and let's convert feet into miles. We're using this conversion factor, 1 mile per 5280 feet. And then let's convert seconds to hours. And notice when we're here, we're going to convert from the denominator to the numerator. So normally we cancel here from numerator to denominator, but here, since this one, we're going to cancel denominator to numerator. That's totally fine. As long as we set this up correctly, we can cancel anything we want. And this is going to leave us with miles in the numerator and hours in the denominator, which is what we want here. A car traveled 60 miles in 2 hours. Okay, 60 miles in 2 hours. All right, how many feet per second? So we're going from miles per hour to feet per second. Okay, so we're just doing a complex conversion. So let's convert our miles to feet. Boom, miles cancel. We're at feet. Okay, now let's do hours. We're going to convert hours to seconds. Now we already know this conversion, but if you had to, you could do it in 2 steps. And then now you have the math all set up. 60 times 5280 divided by 2 divided by 3600. It gives us 44 feet per second. Same thing, we can do the same thing with density. We can calculate, for example, grams per cubic centimeter into kilograms per cubic meter. And when we do that, again, you can either do it in simple steps or you can take, so this is an interesting one because the conversion factor we need to go from cubic centimeters to cubic meters. Well, what we can do is we can take the relationship that 1 meter equals 100 centimeters. So if I cube this, I got to cube this, which means a cubic meter is going to equal 10 to the 6, right? It's going to equal 1,000,000 cubic centimeters. So that gives us this conversion factor. So in the first one, we go from grams to kilograms, canceling out our grams. In the next one, we go from cubic centimeters, canceling up here, to cubic meters, which is what we want down here in the denominator. So our new numerator is kilograms, our new denominator is cubic meters. All right, thank you for your time.